Hello and welcome to this presentation of the STM32H5 Power Controller. The STM32H5's power management functions and all power modes will also be covered in this presentation. STM32H5 devices have several independent power supplies which can be set at different voltages or tied together. The main power supply is VDD, supplying almost all I/Os except those part of the VBAT domain and some I/O pads powered by VDD I/O2. VDD also supplies the flash memory, the reset block, temperature sensor, and all internal clock sources. In addition, it supplies the standby circuitry, which includes the wake-up logic and independent watchdog. The STM32H503 only relies on integrated regulators, while STM32H56X and STM32H57X support either an embedded regulator or LDO or an SMPS step-down converter regulator with configurable scalable output to supply the digital circuitry. vCore supplies most of the digital peripherals, SRAMs and flash memory controller. VDD-A voltage supplies the analog peripherals. Also, USB transceiver and some I/O pads have their own independent power domains, powered by respectively VDD USB and VDD I/O2. See the list of I/O pads powered by VDD I/O2 in the table. It depends on the reference of the STM32H5. A backup battery can be connected to VBAT pin to supply the backup domain. If there are two VCAP pins, such as LQFP64 package, each pin must be connected to a 2.2 microfarad capacitor for a total around 4.4 microfarad. If only one VCAP pin is available, then it must be connected to a 4.7 microfarad capacitor. The STM32H56X and STM32H573 devices embed two regulators, one LDO or one SMPS depending on the package, to provide the vCore supply. The built-in switched mode power supply or SMPS step-down converter is a power-efficient DC-DC nonlinear switching regulator that improves low power performance when the VDD voltage is high enough. The SMPS generates this voltage on VCAP with a total external capacitor of 10 microfarad. The SMPS generates the vCore voltage on VCAP. SMPS requires an external coil. This slide and the next one list the power supplies and related signals of the STM32H5. VDD is the main I/O power supply. VDD-A is the analog power supply and positive reference voltage for the ADC. VDD I/O2 is an independent I/O supply for 9 or 10 I/O pads depending on the exact reference of STM32H5. The VDD I/O2 voltage level is completely independent from VDD or VDD-A. The VDD I/O2 pin is available only for some packages. VDD USB is the external independent power supply for USB transceivers. The VDD USB voltage level is independent from the VDD voltage and must preferably be connected to VDD when the USB is not used. A VBAT input is available for connecting a backup battery in order to preserve the RTC functionality and to back up 32 32-bit registers and 4 KB SRAM. The I/O pads required to use the SMPS converter are VDD SMPS, which is the external power supply for the SMPS step-down converter, to be connected to the same supply as VDD pin. VSSS MPS is the SMPS ground, and VLXS MPS, which is the output of the SMPS step-down converter, to be connected to ground through 2.2 microhenry inductance and a 10 microfarad capacitor. The VREF Plus pin provides the reference voltage to the analog to digital and to digital to analog converters. When the VREF Plus is double bonded with VDD-A in a package, the internal voltage reference buffer is not available and must be kept disabled. VREF Plus is also the output of the internal voltage reference buffer or VREF-buff when enabled. The low dropout or LDO linear voltage regulator is enabled on power on reset. To supply the vCore from external source, it's possible to disable the regulator by setting bypass bit in the PWR SCCR register. In this bypass mode, the internal voltage scaling is not managed internally, and the external voltage value must be consistent with the targeted minimum frequency. Some STM32H5 MCUs embed two internal regulators to provide V-core supply, LDO and SMPS, exclusively enabled by hardware, depending upon package configuration. The following units monitor the power supplies: power on reset and power down reset that ensure proper startup operation without needing an external circuit, brownout reset able to trigger a reset in case of VDD power drop, programmable voltage detector that can be used to detect power drop for any power supply, analog voltage detector that monitors VDDA, VDD-IO2 voltage monitor that checks whether VDD-IO2 is in functional range, and two tamper detection mechanisms: junction temperature monitoring against fixed thresholds and VBAT power supply monitoring against fixed thresholds when VBAT mode is active. The STM32H5 MCUs support dynamic voltage scaling to optimize their power consumption in run mode. Dynamic voltage and frequency scaling, or DVFS, is an energy-saving technique that exploits the linear relationship between power consumption and operational frequency, and the quadratic relationship between power consumption and operational voltage. The voltage from the main regulator that supplies the logic can be adjusted according to the system's maximum operating frequency. Both regulators can provide 4 different voltages and can operate in stop modes. The main regulator operates in the following ranges: VOS 0, V-core equals 1.35 volt with CPU and peripherals running at up to 250 MHz. VOS 1, V-core equals 1.2 volt with CPU and peripherals running at up to 200 MHz. VOS 2, V-core equals 1.1 volt with CPU and peripherals running at up to 150 MHz. VOS 3, V-core equals 1.0 volt with CPU and peripherals running at up to 100 MHz. The embedded voltage regulator implements 3 different power modes: run, stop, and standby mode. In run mode, the voltage is provided to the V-core domain according to the current voltage scaling level. In stop mode, the voltage is provided to the V-core domain to a retention value that ensures that registers contents and memory contents are preserved. Unused RAMs can be totally or partially shut off. In standby mode, the V-core domain is powered down. By default, the microcontroller is in run mode after a system or a power reset. Several low power modes are available to save power when there's no need to keep the CPU running, for example when waiting for an external event. Sleep, Cortex-M33 core clock is gated off, while the remaining parts of the CPU continue to run, particularly NVIC and C-Stick. Stop, based on the Cortex-M33 deep sleep mode combined with the peripheral clock gating. Standby, based on the Cortex-M33 deep sleep mode with the voltage regulators disabled. And VBAT, in which only the VBAT domain remains powered. Each of these modes is going to be detailed in the next slides. In sleep mode, the CPU clock is off. However, all peripherals, including Cortex-M33's embedded peripherals, NVIC and C-Stick, can run and wake up the CPU when an interrupt or an event occur. In sleep mode, all I/O pins keep the same state as in run mode. Software can decide for each peripheral whether its clock is gated off in sleep mode. Wake-up sources are peripherals, interrupts, and wake-up events. The clock sources required to exit sleep modes are the same as the ones active before entering sleep mode. Voltage regulators are active with voltage scaling levels VOS 3 down to VOS 0. Stop mode achieves the lowest power consumption while retaining the content of SRAM and registers. All clocks in the Cortex-M33 core domain are stopped. Stop mode stops all the clocks in the core domain and disables the PLLs, HSI, HSI48, CSI, and HAC oscillators. However, HSI or CSI can be switched on to generate a wake-up interrupt. LSI and LSC remain active in stop mode. The RTC remains active when the RTC clock source is LSC or LSI. RTC interrupts cause the device to exit the stop mode. The user selects which oscillator is used for exiting stop mode, either HSI or CSI. The MCU exits stop mode by enabling an XTI interrupt or event depending on how the low power mode was entered. When exiting the stop mode, the MCU is in run mode, VOS3. The HSI oscillator is selected as system clock if stop WUCK control bit is cleared. The wake-up time is shorter when CSI is selected as wake-up system clock. However, the HSI selection allows a wake-up at higher frequency up to 64 MHz. The voltage regulator is configured by stop voltage scaling SVOS control bits. The selected SVOS4 and SVOS5 levels add an additional startup delay when exiting from system stop mode. The lowest power mode in which the brownout reset is active is the standby mode. In this mode, the regulator, LDO or SMPS, is off and the V-core domains are powered down. The SRAMs and register contents are lost except for registers in the backup domain and standby circuitry. Standby mode stops all the clocks in the core domain and disables the PLLs, HSI, HSI48, CSI, and HAC oscillators. GPIO's state can be retained during standby mode. When exiting from the stop mode or standby mode, the run mode voltage scaling is reset to the default VOS3 value. The microcontroller exits standby mode through an external reset, an IWDG reset, a rising edge on one of the enabled WK-UP-X pins, or an RTC tamper event. The system clock after wake-up is HSI at 32 MHz. In the standby mode, the IOs are by default in floating state. If the IO-RET-EN bit in the PWR IO-RET-R register is set, the IO's output state is retained. IO retention mode is enabled for all IOs except those supporting the standby functionality and debug probe-related IOs, PA13, PA14, PA15, and PB4. When entering into standby mode, the state of the output is sampled and pull-up or pull-down resistor are set to maintain the I/O output during standby mode. After wake-up from standby mode, as long as IO-RET-EN bit is set, the retained state remains applied. Note that the STM32H5 features a separate control bit to activate I/O retention on JTAG and serial wire debug IOs. In the top timing diagram, I/O retention is disabled because IO-RET-EN control bit is cleared at the time the microcontroller enters the standby mode. When software enters the standby state due to wait for interrupt, wait for event instructions, or sleep on exit mode, GPIOs transition to floating state until a wake-up event occurs. In the bottom timing diagram, I/O retention is enabled. When software enters the standby state, GPIO's state is retained until a wake-up event occurs and software clears the IO-RET-EN control bit. In order to help the debug, two signals are available as device pin alternate functions, C-sleep and C-stop. They enable to track transitions to or from run, sleep, and stop modes. C-sleep, when set, indicates that the system is in sleep or stop mode. C-sleep, when cleared, indicates that the system is in run mode. C-stop, when set, indicates that the system is in stop mode, no AHB or APB clock is running. C-stop, when cleared, indicates that the system is not in stop mode, AHB and APB clocks are running. Since C-sleep and C-stop are generated in core domain, they are not driven in standby mode. The backup power domain includes RTC and LSC oscillator, tamper pins, RCC-B-DC-R register that, among others, determines whether RTC clock is enabled, backup SRAM and the 32 backup registers. In VBAT mode, only the LSC is running. The RTC is functional in VBAT mode when it's clocked by the LOC. The backup power domain remains powered on by VBAT when the VDD power is switched off. Switching is done automatically when VDD is powered down. One channel of the ADC is dedicated for monitoring the external VBAT power supply pin. The battery charging is enabled when setting VBE bit in the PWR BDCR register. When VDD is present, it's possible to charge the external battery on VBAT through an internal resistance. This is automatically disabled in VBAT mode. The PWR module has a unique interrupt request that signals an event detected by the programmable voltage detector or the analog voltage detector. The interrupt is connected to the EXDI module. A power drop detected in the VDD or VDDA power domain can therefore be reported to software via an interrupt request. These events also cause an automatic exit from sleep and stop modes. 2 bits are available in the flash option bytes to prohibit entering a given low-power mode. When cleared, these option bits trigger a reset when entering either standby or stop modes. This is a security feature used to reduce the impact of unintentional entry into these low-power modes. If these low-power modes are not used in user code, the option should be enabled. When the trust zone security is activated by the TZEN option byte in the flash memory option byte configuration register, some PWR register fields can be secured against non-secure access. This is controlled by the PWR SEC-CFGR register, which sets secure access permissions to sensitive PWR registers. The following features can be programmed to be accessible only from the secure world: low power modes, configuration of wake-up pins, voltage detection and monitoring, and I/O retention. When the trust zone security is disabled, PWR SEC-CFGR is read as 0, write ignored, and all other registers are non-secure. An inheritance mechanism is implemented for other configuration registers of the PWR module. When the system clock selection is secure in RCC, the voltage scaling or VOS configuration is secure. When the UCPD1 is secure in the Global Trust Zone Controller, the PWRU CPDR register is secure. In addition to this training, you can refer to the following presentations: Reset and Clock Control, Real-Time Clock, and Tamper. See also the application note AN4938 for further explanations about the STM32H5 hardware development.